All right, thanks everyone for coming. So yes, my name is Jimmy Bogard. You can find me on Twitter at @jbogard. You can find this presentation and all the presentations I do on my GitHub at github.com/jbogard. And I blog about this topic and a lot of others at my blog at jimmybogard.com. So my day job is building custom applications, mainly the .NET space. And part of my job is kind of helping customers when they're trying to build new systems and they're on top of an existing system, and we're really kind of a greenfield, starting things from scratch. But sometimes we're brought in a little bit later in the process where some teams are having a little trouble and they're trying to cross the finish line and they just need some kind of some push to get there. So this is a story of one of those customers who had 6 little lines of problems about 2 weeks before they were supposed to ship. So I work with a coworker, his name is Bill. His name is actually Bill, I didn't change his name. And he's one of those guys that's just like super calm and chill and stoic, and like nothing ever phases him ever. Like really hard to shake him, really hard to get him worried. And so I was just sitting at my desk one day and Bill came over and he had this like really worried look in his face, almost like sweating in his face. And he's like, Jimmy, I've been reviewing some code for a customer about to go live, and I saw some stuff that's got me a little worried. And normally when a developer comes in and they get this worried look in their face, they're usually like blowing it out of proportion, so I have to kind of calm them down. But Bill, who like never shows any emotion, if he looks worried, then I'm thinking, oh crap, something's really, really wrong. So I said, okay, Bill, let's go grab a conference room. This is back when we all worked in offices. So it's been a while. And so let's go grab a conference room. We'll sit down. Let's put the code on the screen. Let's just walk through those steps one by one. And he showed me 6 little lines of code in this code base. Now these 6 little lines were the most important lines of code in the entire code base, because this was a website that took orders from customers. And eventually you get to the last page in the order process and you have to hit the most important button, which is the button where you submit the order. And that button is the way that the company gets money. And if that button doesn't work, the company doesn't get money and the company goes out of business. So it's like the most important lines of code in the entire code base, the code that takes your money. So he showed me this. It's okay. It's pretty simple code, but I think it's got some problems. So let's go take a look. So it looks something like this. This is an ASP.NET Core application. So this is something like the controller action or whatever that actually takes the button click of you clicking the button on the final page of the process, submitting your cart to process your payment. So it shows me the set of code. I said, okay, let's walk through this one by one. So the first step in the process, we take your cart information and we go to the database and we load your customer information based on your cart. Okay, that's simple enough. Then we go ahead and create an order based on your cart information and your customer details. So those 2 things put together, we create an order from them and we go save that into the database. This is where things get interesting. So after we save your order, well, we have to charge you for your order, right? So in this case, they're using a payment gateway known as Stripe. And so they went ahead and just called a Stripe API to go ahead and post a payment to that third-party gateway to be able to process your payment. Okay, now that we've successfully taken your money, then we're going to send you an email saying thank you for your order. So in this case, we used another API with SendGrid and called their API to go ahead and send you that thank you email. Now the final couple steps in the process, we can't process the order immediately here. We have some downstream order processing and fulfillment that has to happen. So in that case, we're using messaging to do so. So we're using RabbitMQ to publish an event that says order's been created. Now downstream systems go ahead and do your thing to process that order and actually ship it out to the customer. So once those steps are completed, we redirect the customer to one of those generic thank you pages. It's got your order ID there, probably has a link to go view the status of your order, and everything's good to go. Now outside of all of this, there's one thing we couldn't see here, is that as part of every request that we do that changes information, we're doing transactions. And everyone's doing transactions, right? Yes, hopefully. And so somewhere in our code, we've got some middleware that saves the changes and submits the transactions to the database based on every single post request that we do. So it's somewhere in middleware somewhere. So I saw this and said, okay, the code isn't wrong, but it's not necessarily right, because there's nothing in any of this code that we see that handles any of one of these steps going wrong. So if any one of those lines of code throws an exception for whatever reason and fails somehow, there's nothing in this code that can handle that situation. And so since this is the most important 6 lines of code in the entire code base, where we're taking money from the customer, we should probably deal with failures in each one of these different things that we're calling out to. And that's one of my mottos that I stole from a popular TV show here in the States called Mythbusters, where they do experiments, and part of their experiments, like half of them fail. And they have the saying that failure isn't always an option, that things will go wrong in your systems. And especially when we're dealing with distributed systems, as I start to connect more and more pieces together, then it greatly increases the chance of something going wrong. And if our code just assumes that everything is always working all of the time, then when something does go wrong, then our system can behave in bad ways. So the first thing we need to do is figure out, okay, what's the scope of this, of the impact of a problem happening in one of these systems that we talk to. So how bad, how worried should Bill be? Basically, how much should he be sweating? So we mapped out the set of calls on the whiteboard. So, okay, there's a basic set of calls that happen. We have to make this call to the database. We have to call these other systems and services to do the work that we need to do. So let's just take these calls one by one and ask ourselves, what happens when this call fails? I'm using the language there very carefully. I'm saying when, not if, because if I say if, then everyone interprets it as like, well, that means there's some possibility that it will succeed. So let's just pretend that it always succeeds. And if it fails, like that's probably a really remote chance. So we probably never happens, right? That's not true. Like Google goes down, Azure goes down, GitHub goes down. Like this happens all the time. And if these really big companies can't stay up 100% of the time, then there's really no hope for the rest of us. So we need to go through each one of these different calls and understand, well, what is the impact to the overall system and what's the impact to the customer? You always have to keep them in mind as well. So let's take this first one. What happens when this first call to the database fails, which is I am grabbing the customer details out of the database and I'm inserting an order into the database? Well, now this is a pretty remote chance, right? Like if our database isn't working, then probably nothing is working. So we put a lot of resiliency in that database, have high availability, like redundancy, all that sort of things. But just, let's just see what happens here. So in that case, the exception happens very quickly and the transaction never succeeds. The error is shown to a user, so they see like something went wrong with your order, but at the very least, the system is consistent. So everybody agrees that the order never went through. Now, obviously not an ideal experience for the end user to see like an error screen on the page they just put their credit card information into. So we probably want to make sure that that doesn't fail for those reasons. But at least like we didn't accidentally take the money or there's some order in the data or something like that. So everything is as it was before, but the customer's probably not very happy and they probably won't come back. All right. What about Stripe? What happens when we call Stripe and Stripe's API is down? So in this case, we've inserted a row into the database. However, that isn't a transaction. So the transaction would roll back, no money would post. And so at this point, the system is still consistent. That is, there's no order in the database, and Stripe also agrees that we don't have any, we're not posted any payment over there because it failed. Okay, now this is where things get interesting. So we said, things are okay when the database is down, things are still working okay when Stripe is down. What happens now when SendGrid is down? So we have inserted the row into the database. However, that's in a transaction, so the transaction rolls back. However, the call to Stripe succeeded. So that means that the customer was charged, but the transaction rolls back. So the customer sees that error page and says, oh, okay, well, I guess I'll try again later or whatever. But then a few days later, they check their credit card statement and notice like, wait a second, I've got a charge against my credit card for the order that failed. So they contact customer service and say, you charged my credit card, but my order didn't succeed. It's okay, but do you have an order number? Well, no, because I never got to the page that showed me my order number. So again, the customer service rep is annoyed, like stupid developers can't build a system that works, and so they'll go give the customer their money back, maybe give them a discount on future purchases. So the customer isn't happy, probably going to Yelp, writing bad reviews, all that bad stuff. So what happens now when RabbitMQ goes down? Which it can go down. Like, it's not a completely 100% system, these messaging systems. So what happens when RabbitMQ goes down? Well, those when things are getting much worse. You can kind of tell, like, as we go down each step later in the process and they start failing, things are in worse situations. So enter the row in the database, make a call to Stripe. Call to Stripe succeeds, so we've charged the customer, okay? Now we make a call to SendGrid. SendGrid succeeds, so the customer actually receives an email, thank you for your order. However, RabbitMQ fails. That throws an exception, which means the transaction rolls back and that order is never inserted into the database. So the customer is charged, they're notified with an email, but the transaction rolls back, so the order doesn't exist in the database and the system is inconsistent. Now when they call customer service, it said, you charged my credit card. Okay, what's your order ID? Here's my order ID because you sent me an email thanking me for my order. But when I click the link in the email to go to my order, it says 404 order not found. Well, that's odd. So the customer service rep, so they look it up and then the admin tool and say, yes, that's right. There is no order with that number that exists in the database. So again, like, really bad situation. We have to make it good with the customer, give them a discount, hope they're happy again. But they're probably not. They're probably going on Yelp and writing more bad reviews for us. So things in a very, very bad position here. So what happens now if the transaction fails? Now, this can happen for a number of reasons, right? Like, it could be something that we are protecting against. Maybe it's a constraint violation. We have something like cannot insert duplicate order IDs, or we cannot insert duplicate customer username, something like that. So it could be some constraint violation that causes a transaction to error out. Or it could just be, we're using Azure, and Azure SQL has hiccups sometimes. And so maybe there's just some transient problem that causes the order to have a hiccup and we couldn't insert that row into the database. To this point, our system is royally screwed up because we have successfully charged the customer. We have successfully emailed the customer, thank you for your order, and now we've actually notified downstream systems to process an order that doesn't exist. So we've charged them, notified them, and now downstream systems start to process an order that doesn't exist in our database, so now the system is just royally, royally screwed. So that was a question that we had to ask ourselves, is this can go pretty wrong, and we can't just assume that everything's going to work, so what do we do? Well, what does the code do now? Just kind of throws up his hands. Well, we'll just hope for the best and see if everything works. But just shrugging your shoulders and hoping for the best is probably not good for the business. And hope is really not a strategy when we're trying to deal with these sort of problems. So we have to figure out, okay, based on each of these different connections failing, what are the appropriate ways we should deal with those failures? Well, the real problem here, right, is that our transaction is just the database, right? The transaction line right there, it just goes around the API and the database. So what if we just made everything succeed or fail all at once? What if we extended this line of the transaction from the database and just flip, just move it. There we go. So look, that's perfect, right? Now everything is in a transaction. So now everything either succeeds or fails. Well, people have tried this. And for those of us that have some gray hairs, have probably had to deal with these kinds of APIs that try to extend that line out. And so in the early mid-2000s, a bunch of companies got together and tried to build transaction protocols on top of web services. And they had, 4 different protocols that they put out there to try to get them to work. So you had things like WS transactions, WS reliability, WS reliable messagings, and then a couple others too. They're all trying to say, what we need is just more guarantees between all these different communications. to ensure that I can either all succeed or all fail. But it just doesn't work. You can't put the world in a transaction. That's actually not how the real world works. Like when you go perform that kind of transaction in the real world, it's not like everyone gets in a room, in a conference room, and says, okay, everybody good to go. We're gonna do this transaction. That's just not how it works. The real world is much, much messier. So for our systems, because nothing is ever 100% up all the time, we have to assume failures, assume that things are gonna go wrong, and plan for the worst. That is, look at each one of those different pieces in our diagram and say, what happens when each one of those fails, and what are the different options for dealing with those failures? Now, luckily, there are people much smarter than me that have looked at these sort of problems and try to come up with some strategies about how to deal with those sort of failures. And there's a great paper out there from Gregor Hope titled, Your Coffee Shop Doesn't Use Two-Phase Commit. And two-phase commit is what we're trying to do if we say put the world in a transaction. And so he went to a coffee shop. Actually, this paper used to be titled Starbucks Doesn't Use Two-Phase Commit, but I guess Starbucks didn't want to be associated with like failures and stuff. So now it's just your coffee shop doesn't use two-phase commit. And what he observed is that if you look at real world distributed systems, the interactions and failure modes are much, much messier than what we're trying to build in distributed systems. So if we look at those real world systems and try to see what are the different strategies they use, maybe those kind of strategies we can apply to our systems as well. And so in this paper, he outlined 4 different options for dealing with failures between 2 or more systems. So let's look at these options one by one. So the first option, it would be to ignore the failure. So I make a call to resource A, I make a call to resource B fails, and we just don't care. Say, well, we tried, let's just move on. You might say to yourself, well, we should never ignore failures, right? Well, we should never ignore them, but we could consider the possibility of ignoring it in respect to processing our action. A good example of this would be, do I want my system to go down if my logger fails? So let's say the logger writes to disk and the disk fills up. Do we want our system to go down because logging can't work anymore? Probably not. We should not ignore it in the grand scheme of things. So someone should be notified to say like, don't log to your local disk, log to somewhere else. But otherwise, those inconsequential actions shouldn't necessarily bring down the entire system. So this is something we should at least consider depending on the action. Option 2 is to retry. So we make an action to resource A, we perform an action to resource B fails, and we simply try again. Now I say simply, it's actually more complex than that because we can't retry forever. Like, how many times do we retry? Do we retry just once? What if it fails again? And it fails again, it fails again. Do we wait a little bit? How long do we wait? If it's a resource with a lot of contention and a bunch of things keep retrying, that can actually make the system worse. So we have to put a little bit of thought into exactly how that retry should happen. The other thing we need to worry about is resource B able to be retried? So if I try the action again, do I know it actually succeeded or failed the first time? Or do I need to check to see if the first time actually succeeded? Okay, option 3 is to undo. So I make an action to resource B, A, I make an action to resource B fails, and now I undo the action in resource A. And this is a logical undo. So this assumes that resource A succeeded. So like in a database, you assume that the resource A transaction has succeeded. So the undo action has to be a logical undo. So I need to figure like what that action was and to try to perform another action that reverses the previous action. So if you ever use Git, right, you can't undo a commit, but you can revert a commit. So when you revert a commit, it's a new commit that undoes the actions of the previous commit, but it's another commit on top of your commit log. And it doesn't go back with an eraser and try to erase out the previous commit. So depending on our action, we need to understand what is the logical undo of whatever the action represented. Now the final one is to coordinate the activity between those 2 resources. And so the idea here is that we do get resource A and resource B in a room with a third party to both talk to each other to agree that this action can succeed or fail. And it starts out with two phases. The first phase being a prepare phase. And so you have this third-party coordinator that talks to resource A and says, hey, can you do this action? And waits for resource A to say yes or no. Then it asks resource B, can you do this action? And waits for resource B to say yes or no. And during that time, resource A and resource B prepare the transaction. So they're kind of putting it to the side, waiting for the next acknowledgement to say, go ahead and commit the transaction. So it's not just a thumbs up, thumbs down. They're actually like setting aside the resource to say, oh, yes, let me go ahead and put this to the side so that I can commit this transaction in the future. The coordinator, once they've received the feedback from both resources, then goes to the second phase of the commit protocol, which is to tell each resource to then go ahead and commit. So it will tell resource A, go ahead and commit, and resource B, now you can go ahead and commit. Now this isn't a bulletproof transaction protocol. There can be, you notice there's like way more lines in this one now. So there's a lot more communication that has to go back and forth. And that also means that those are additional lines that can fail, that can go wrong. So we need to make sure that, yes, we've got very low latency between the coordinator and those resources. So we can talk back and forth very quickly. And if something goes wrong, we need to be able to recover from that failure. So part of the way this protocol works is if the commit protocol fails, then we have to be able to eventually succeed in each of those different resources, which could mean locking resources indefinitely. So if resource B failed and got retried, but someone else came and tried to do something later, then like, well, like these things are contending with each other, but I have to make sure this other one goes through. And so it introduces a contention problem. It's also much more expensive because you can see those different lines going back and forth. And so you look at that and say, why would anyone ever do this? Look at all those lines, look at all those reasons to fail. And in real distributed systems, we do try to avoid that as a protocol. That is, we do try to avoid this highly chatty sort of communication back and forth. But there are some cases where we can achieve it using application level protocol. And you actually see this kind of communication pattern in the real world. If anyone here has ever had to purchase a home or a condo or any kind of real estate, you have a buyer and a seller. And the buyer and the seller don't necessarily talk directly with each other to agree on a price and the terms and conditions of selling the property. Instead, we have this third-party real estate agent that is going back and forth between these two resources to be able to broker this sale. And they're not cheap, right? They take, I don't know, some commission. And so they're not cheap in the real world, and they're not cheap in our distributed world either. So our master plan is to look at each of these external resources, examine the possibilities, and pick the best option based on our business requirements. Now we have to blend the business and technical requirements together because we can't just pick based on what the technical merit is, because that could ignore some impact to the customer. And we can't just pick based on the business requirements because that could ignore the technical possibilities, and they could pick something that's just impossible to actually implement. Because if we went to the business and said, which one of these options would you like? They'd probably say, I want it all to succeed all the time. And the answer of like, well, better get out your wallet is, doesn't go over very well, because they don't ever want to pay for, 17 nines of uptime. They want probably 3 nines. They want the 2 nines price for 5 nines, but that's just never reality. Okay, so let's look at these one by one. First up is Stripe. So just a refresher, Stripe is the third step in the process here. So we read from the database, we write to the database, and then we call out to Stripe. Option 1, ignore. So ignore, just be like, try catch, call Stripe, it failed, let's just keep going. Well, we probably don't want to ignore a failed payment because we actually want to make money as a business. So this may not be one we bring up to the business as like a potential option available to us of like, well, we tried to take your money, but it didn't work. But hey, you get your order, everyone's happy, right? Well, no, the accounting people aren't happy because we're losing money. Option 2, retry. Now this one we have to be careful about because we're calling a web service API. And a failure there could mean that the API is down. And then we get like 500 gateway something, we can't actually contact the other API. Or it could mean that we tried to call your API, we waited, and we waited and we waited, and we gave up because we never got a response. But that doesn't necessarily mean that the other side failed. It just means we didn't wait long enough to receive an acknowledgement that it succeeded. So the Stripe call actually could have succeeded, but we saw it as a failure. So if we retry, we want to make sure that we don't accidentally double charge the customer. And there's a fancy scientifically or computer sciencey term for this, the ability to retry an operation multiple times, but only have the outcome of that operation done once. This is known as idempotency. And so what I do is I Google the name of the name of the service, Stripe, and then I Google idempotency. And luckily for me, Stripe actually has a nice documentation page that describes this is how you do idempotent requests. So for anyone out there doing payment gateways, like do this. If you get nothing else, like do this stuff with your APIs if you're calling payment gateways to make sure you don't accidentally double charge customers. And so there's two different ways that you can deal or be able to handle idempotency. The first one is I get a request and I get another request, and the recipient is able to look at those two requests and say, oh, these are naturally idempotent because they represent the same operation. And a good example of that is to say like a request to turn the light on. So if I go to turn the light on twice, like, well, if it's already on, there's nothing to do. Like I can't, it's not double on, it's just on. But that's not always the case. And a good example of this is charging a customer. So if I charge a credit card and I charge a credit card again, I need some way to know if those two are the same request to charge a credit card. And I could either look at like all of the information inside that request and say, well, this one obviously looks like the other one, so they must be the same request. And the other option is to say, let's just include some identifying information on that request so that when I receive another request, I can go look at that unique identifier somewhere to say, oh, I've already done this thing. So Stripe has that. If you send in an idempotency key that's unique to that request and to all other requests, then they will look up at their side, have I already charged the customer based on this request key? And if they have, then they won't do anything. They won't double charge a customer. So we go back and look at our API calls and say, well, what on this set of calls represents the unique request to charge the customer? And so we actually have that. It's the cart ID. The cart ID represents that unique request to charge a customer for some transaction. Once you click submit order, we charge you for that. We charge you for the products you put in your cart, but then your cart empties and you get a new cart, or that cart gets thrown away. So the cart only lives for the lifetime of your transaction, and once that business transaction succeeds, your cart goes away and is no longer valid. So that cart ID represents this distinct request to charge you for these products. Okay, option 3 is to undo. Now this one's a little trickier. Like the previous one, I can just Google Stripe idempotency and I can see a solution. You can't really Google Stripe undo. There's not like a nice Google term that you can put in there and be able to get a good response. So you have to kind of think about whatever operation you're doing, what is the logical undo of that operation from the business perspective or the domain perspective? So what is the logical undo of charging you? The undo for that would be a refund. A refund gives you back the money for a previous charge, but it's a new transaction that shows up in your account. And you'd see that in your credit card statement. You'd see, like, here's your charge, and then later on, here's another charge that is putting the money back into your account. And so Stripe handles this with refunds. The refund, I have to give it the original transaction ID from the original charge, and it will put the money, the exact amount of money, back into the customer's account. So I could do it something like this. I could put a try-catch around all of those lines of code of doing the important work, and then if something fails, then go ahead and call Stripe to say, go ahead and refund that payment. Now this isn't all of those 6 lines of code. We're missing one, which is the database transaction. So in this case, because we're doing other things that are more complicated, let's go ahead and bring in the database transaction commit so that I have everything succeeding or failing all together. So now I've got, if something goes wrong, then I will refund the payment and I will roll back the transaction. So at the very least, Stripe and my database agree on the state of the system. Option 4, coordinate. Now, I said before that we don't want to do distributed transactions. We don't want to do two-phase commit, which is true, but there are some cases where an application level coordination could be a possibility. And this is actually something that is possible with payments. And you may have noticed this if you go to your bank statement or credit card statement. You may see at the top a set of authorized transactions that have not yet posted to your account. So those are things where someone has said, I would like to take your money, and they kind of put their finger on the money. And what that'll do, though, is kind of put the money to the side. It's not taking it right away, but it's putting it to the side so that no one else can take that money out of your account. And so this is kind of a two-step process where they first authorize the payment, and then they capture the payment, and they actually take your money. And so this also exists with Stripe. It's a two-step payment flow where they first authorize and then capture. And you can see this all the time. You go, well, I used to go, but when I did go to a hotel, the first thing they do is they say, can I have your credit card? But I already paid for the hotel, so why do they need my credit card? Well, we need your credit card for incidentals, which is, me going to the bar and ordering on my tab on my room. And what they want to do is just say, I'm going to take some money out to just make sure that you can pay for something. That way we don't lose money when you just up and leave and never see us again. So it's a thing in the payment industry to be able to authorize charges and then capture them later. So more try catches. So now we've got the first step, which is to authorize the payments. And if everything succeeds, as I don't get an exception, then at the end, we will go ahead and post the payment and capture it. And the nice thing about this is in the normal order, the normal flow of things, the customer will never see the authorization of their payments hit their bank account, because it would happen so quickly, like authorize capture, authorize capture. But when something goes wrong with the capture step, then we could have an administrator go in and say, oh, here's a bunch of charges that were authorized but never captured, so let me just go ahead and click that button, capture them, and we're good to go. All right, next up, SendGrid. Now, SendGrid is like the polar opposite of Stripe. Stripe is all about, this is a very important API. We, going to put all these guarantees in place to make sure that you charge your customers correctly. SendGrid is more like, I'm going to send the emails as quickly as possible. Like, you call my API, boom, email's out the door, done. Just like as fast as we can do it, the email is gone. So they're going to have a lot of different guarantees with their APIs than with Stripe. So let's go through these steps again, one by one, to see what are options and how that would actually work out in practice. Now, option 1, ignore. Okay, now this could be a possibility. Do we have to send the email when the user clicks that button? Do we want to fail the order if we can't send the email? Probably not. So in this case, it could look something like this, where we just put a very simple try catch around calling SendGrid. And if SendGrid fails, then what we can do is still log an exception. So like an administrator can go and the trusted administrator that is monitoring the exception logs, and then go like, oh, something's wrong with SendGrid. Let's go figure out what's going on and fix it. And if the customer actually does need that email, then we can figure out some other remediation plan. Option 2, retry. Okay, so this is where we go, okay, let's go ahead and do this. SendGrid item potency. And our results are basically like Stack Overflow questions with 0 answers, but a lot of comments. People also asking the same question in the comments. And we know that if we find a question on Stack Overflow with no answers and only comments, we're in a very bad spot. And so that's what we have here. There's no such thing as item potent emails. So as much as we wish there were. So if I call SendGrid twice, the customer will get 2 emails. So we don't want to retry unless we want duplicate emails. So this is where I go back to the business, right? Like, do you want duplicate emails? No. Okay, well, do you want the customer to get no emails? No, we want exactly 1 email, but that's impossible. Option 3, undo. Oh, how I wish I can undo an email, but we can't. Once we send a message, the message is sent, and that's it. It's something that some email clients try to get around by basically well, let's put the email in a local draft for like 10 seconds, and you have like a little bit of a window. But once that email is sent, though, it's done, it's gone. So as much as we want to, we can't unsend emails. And so what's the logical undo of an email, like sending an email? Thank you for your order. Here's your order number. Then 30 seconds later, just kidding. There's no order. So sorry. Really, it's like, apologize. We're sorry we screwed up your order. We'd love to have you your business, so please try again. I've definitely had to write those emails. Like, I've introduced some bug into a payment system. They go wrong, and then I got to help craft the email to apologize to customers. But that could be a kind of a business level undo, because we can't recall our email and get it back. Option 4, coordinate. I don't even know what this would look like. Like, I put my finger on the email and I go some other system, like, hey, everybody, kind of payment good, database good, okay, let's go ahead, and boom, now the email gets sent out. So that's just not a thing with really any emails. Like, you don't have any kind of two-phase commit with emails. It's just not a thing. The final one is RabbitMQ. And this one will look very similar to SendGrid, because it's also messaging, right? It's just the nature of the message is a bit different. I'm sending it to downstream systems for automatic processing versus sending an email to a human that they can read and then do what they want with it. So option 1, ignore. This is a tough one. Like, we do need to process the order, but the question could be, do we need to process this order now, or can we wait for it in the future? Or can we try to process it now? And if something goes wrong, let's have something that can do it in the future. So we could do something like this, where I will try to publish the event via RabbitMQ, but if something goes wrong, then what I'll do is just flag something on the order to say, hey, this thing needs its message sent sometime in the future. And then I can have some kind of background process that is just looking for orders that need their messages published, and then go ahead and publish them out of band. So I try to do it ahead of time, but if it doesn't work, then I'll do something offline to catch up. Not a bad solution. Option 2, retry. So again, we have to look at the nature of this. And we said that if we are doing retries, we have to make sure that the thing we're retrying on top of can handle duplicate messages. And if you look at RabbitMQ and Google RabbitMQ idempotency, again, we're in the land of Stack Overflow questions with no answers and a lot of comments. RabbitMQ does not support idempotent messages. It does not support exactly what's processing at all. Some brokers do, so like Azure Service Bus can do this within like a specific window. They can try to deduplicate your messages. That's like 10 seconds, so not a very long time. So if our broker can't do it, then we have to look at, well, what about the downstream systems? Can those things, whatever they are, can those downstream consumers handle the messages arriving more than once? And so I have to go with these integration teams. It's like, hey, can you handle this? Whatever. And they're like, please don't send us multiple messages. We just want to process the order once. Thank you. So I look at this and say, well, okay, I can retry the message, but it would only work if all my downstream consumers can handle duplicate messages based on whatever they're doing. Option 3, undo. Okay, this is even weirder now because we can't unsend a message, just like we can't unsend an email. So we have a message going out, order succeeded event, and then what's the undo? Haha, just kidding. No order succeeded, order actually failed event. So a compensating message would be a bit weird, and we'd have to craft an entire business process around doing that. And the final option is coordinate. And again, like, can't coordinate. You can at most do like a acknowledged messages. So you send a message, but then you have to get an acknowledgement that was actually sent. But most brokers don't support any kind of coordination between multiple resources. You would have to do this completely on your own. And again, it'd be very expensive to do because you're now having to coordinate all these different resources with additional communication. So Bill and I were not in a very good spot at the end of this meeting. So we took a break and said, oh gosh, all these different options, all of these require some communication with the business to understand what makes the most sense. And each of the different code options we're looking at was looking at things one at a time. if we try to fold in all these different scenarios together, that would look just completely messy. So Bill and I said, okay, let's take a few hours, let's take a break and take a step back. Because I think part of the problem here is that we're trying to do too much at once. That we've got a lot of process coupling because we're trying to do everything with an order in the context of a single button click. So can we avoid the exceptions by just breaking the process coupling and stop trying to do everything all at once? So we look at each of these steps and ask ourselves from the technical perspective and ask the business from the business perspective, do I have to do each of these steps now, or can I do them later? And if I can do them later, then it could benefit us from breaking up the process coupling and trying to do everything all at once and handling the failures of partial success and partial failure. So we go by one by one. Do I have to charge them now, or can I charge them in the future? And Mrs. could say, well, in order to complete their order successfully, we don't have to charge them now. We could charge them later, but we'd like to try. We want to take their money, earlier than later. So it could look at something like this, similar to our RabbitMQ option, where we try to post their payments, and then if something goes wrong, we mark the order payment as failed, and then we have some offline process that looks for orders with failed payments and tries to process them out of band. What about SendGrid? What is the thing that should trigger SendGrid sending the email? Is it me inserting a row into a database? Well, not really, because it's, thank you for your order. We just inserted a row isn't necessarily the truth, right? We really want to wait till we've actually successfully charged the customer to then send the email. Because when we've taken your money, that's when the order is truly successful from a business perspective, not necessarily when I just inserted a row into a database. So we could say, okay, SendGrid shouldn't trigger off of inserting a row into a database. It should trigger based off Stripe succeeding. It turns out Stripe actually has those kind of triggers associated with it. That is, instead of me having SendGrid and Stripe all in the same block of code, instead I could physically separate those out so that I call Stripe and then keep on going. And then Stripe, when something succeeds, it can use a webhook to then call into my API. It can then go call SendGrid. So we did actually look at this, but we didn't have a lot of documentation about how like retries would work. We didn't want duplicate emails to go out necessarily. We wanted to check the status of the order. So we looked at this, but it was going to be a little too complicated for our scenario, so we threw it out. But still a valid scenario to, if I want to have actions trigger another action, then webhooks are a way to do that so they don't have all of the actions in the same block of code in the same unit of work. What about RabbitMQ? Do I have to send the message now, or can I send the message later? And the idea here is that if RabbitMQ goes down, then I don't want it to fail my entire transaction. Or the other thing I don't want to have happen is I send the message to RabbitMQ, but the transaction fails. So I have a message that goes out the door, but there's no order that it can be associated with. So this is a well-known problem in the microservices service-oriented architecture, where I'm trying to coordinate two activities of a database activity and a messaging activity. And the way we could address this is, instead of me sending the message right now, I actually create a table in my database that represents the messages I want to send in the future. And since I'm already using messaging that is already asynchronous, it's not a huge leap to say, instead of me calling the broker directly, let's just put them in a little table, and then something goes and looks at the table and then sends those messages out the door. So that is known as the outbox pattern. And in the outbox pattern, my senders insert rows into a database that represents the messages you want to send. And then we have a background process that is looking at those rows in the database in an outbox table. And then we'll go ahead and then translate those messages to transport, whatever RabbitMQ Azure Service Bus, and then finally send them out the door. So the rows for the messages are part of that overall database transaction. So the quote sending of messages either succeeds or fails based on my business database transaction succeeding or failing. So it looks something like this. And instead of me calling the bus or broker directly to send a message, instead I will call into my data access code to insert a row into a database that represents that message. So you can kind of imagine behind the scenes, it will save some information or probably serialize this thing to JSON or something like that to save it into a row in a database so they can eventually go out the door. And then behind the scenes, something is watching that table, well, somewhere that's like just looking at the messages in the database in that messages table. And then for each message we see, go ahead and send those messages out the door with the broker. But we're still not there. We still have a whole lot going on in the context of a single button click. If I started folding in all of those tries and catches and like failure flags and stuff, it's like there's a ton of process coupling and process logic mixed in with the business logic of processing an order. It's all like this workflow stuff all mixed together. So we looked at it and said, okay, this is not how modern e-commerce systems work. They don't try to put everything in your button click. They try to separate each individual action and operation into its own kind of logical unit of work, and then they use something else to coordinate all these different activities together. So we look at how modern e-commerce works. They use background processing to fulfill orders. When you go to like Amazon or whatever, and you click submit order, that is doing as little as possible to be able to take your order information. Everything else behind the scenes to fulfill your order is done 100% offline. And we would see this as well. I was part of an e-commerce team. My team was the cart checkout page. And we even went as far as to turn off all validation. So we just had to make sure that the required fields were in there. But it could have been your cat stepping on the keyboard, and we would take that order. The idea being that it was anytime we showed red, those validation errors on the checkout page, people would get mad and quit. So I don't want to make you mad when you're trying to give me money. I want to make you happy. So I will try to make it go as smoothly as possible. You give me information. If something goes wrong, we'll call you. And that's what we did. We had order processors. There were background processors like services behind the scenes. And we had order processors that were humans that would call you in case something went wrong. So we need to put all these steps into some kind of workflow. To understand how to build that workflow, we had to look at what were the different process constraints between each of these different steps. So Stripe, for example. Stripe, we saw, we went to the business and said, do we need to do this now or can we do it later? They say, well, if your credit card gets denied, we don't want to show you that. We want to, we want to see that error message first, and then call you and say, be nice about it. Say, it looks like you may have mistyped your credit card, or whatever it is, to be really nice about it, so that we can eventually get your money. So that is okay to be processed offline. The same thing with SendGrid and RabbitMQ. All of those things can be processed offline. The only thing we need to do is just take your information. Everything else can happen completely offline. So we do have to kick this off. Like something has to start this whole process. So we could have things like Hangfire working in the background, some kind of background cron job that's going, that is looking for all my messages in my outbox, or they could be looking for orders that need processing. There's a flag on the order to say this order needs processing. So something is in the background to be able to kick things off and start the order processing, start the order processor. So request comes in, inserts were in the database, something is going on behind the scenes to go ahead and forward that out to an order processor. And now I got to figure out, how do I coordinate these different downstream services together to be able to fulfill an order? So in this case, we started to look at the different workflow patterns available to us when we start having these asynchronous processes. And the simplest one out there is known as the routing slip pattern. And the idea behind a routing slip, and it comes from manufacturing, is that the first step in the process looks at the order or the request and says, okay, based on this information, these are the 3 steps that need to happen to fulfill this request. Or it could be that there's 4 steps. This order needs 3 steps, that order needs 4 steps. And what they'll do is they'll write that on the order, on the request, as the list of steps that need to happen. Then each step of the process receives the message, does its work, then it crosses its name off the list and looks at the next name on the routing slip and forwards that message on to the next step. So it's not making any complex decisions about where to go. Those have already been made up front. All it's doing is looking at the next destination on the list and forwarding that message on. So it looks something like this, where the message initially gets sent to the Stripe endpoint, which is now processing asynchronous messages. Stripe does its work and forwards it on to the next step, which is SendGrid. SendGrid does its work, forwards it on the next step to RabbitMQ. So at the onset, it's just a single call to say, go ahead and route this message to these destinations, and each of those destinations would process that message one by one. Now, this works for simple scenarios where I don't have to do a lot of workflow processing with each individual step, but it doesn't work for more complex scenarios where there's dependencies between steps or need to handle failures. So in that case, we can start to look at more complex workflow patterns. And one out there is known as the saga pattern. And the saga pattern is a pattern in which we have a series of forward transactions and a series of reversal transactions. And so the saga is trying to coordinate a distributed transaction with a series of smaller transactions. And each of the smaller transactions has a forward transaction and an undo transaction. Well, in order for this protocol to work, you have to have reverse transactions, but we've already seen that not all of the steps in a process have an undo. So for us, the saga won't work. Well, the last one in the list is just the generic process manager pattern, which is basically you just have like this thing in the middle that sends and receives messages from different endpoints and coordinates the activities between them. So it's basically like you're on your own basically to figure out how to coordinate these different things together. Well, it turns out there's actually two major patterns in process managers that folks use to be able to design messages and coordinate activities between resources. And that's known as orchestration and choreography. It's also kind of command-based or event-based. So orchestration is more command-based. I'm telling each step what to do. And event-based is I'm notifying a lot of different endpoints of things to do, and there's no dependencies between those, so I just wait for them to come back. And how I know to choose between which of these is to look at each step in the process and see if there's any process dependencies between each of those steps. So the first one, Stripe. We asked the business, like, is there any dependency between Stripe and anything else? They say, yes, like charging you has to be the first step. So if I have to make something go first, then I'm going to orchestrate that call and make sure that happens before anything else in the process. And what about the others? Well, once payment has succeeded, I don't have to do the other steps in any short order. That is, I can email the customer and fulfill their order at the same time. There's no kind of coupling between those two steps. So in this case, I actually have a mix. I have something that has to happen first, and then other steps that can happen at different points in time without any coordination between them. So our final picture looks something like this. We have the initial post from the customer that says, I want to place my order. And the only thing that does is insert a row into a database, and then that's it. The customer sees the thank you page, they're done. Once that is completed, there's a background task that is looking for those orders to process, whether it's an outbox or just flagging the order, whatever it is, it's looking for those things and forwarding that message on into our process manager. So the code looks something like this, where we create the order from the carts, we insert the order to the database, and we send a message to our downstream system to say, go ahead and process this order. Once that process manager receives that information, it's going to send the first message out to Stripe to say, go ahead and process that payment. And so the process manager is going to receive the initial command to say, go ahead and process your order, and going to send a message out to Stripe to say, process that payment. And then Stripe receives that message in a handler, receives the process payment command, and then at this point, now it's just going to go ahead and call out to the API gateway to Stripe to go ahead and process the payment. It can look at the result of that and then report the result back to our process manager to say if this succeeded or failed. So now the process manager has received the results of that operation from our Stripe gateway that is managing the communication with Stripe. I've received the result of that and now can decide what do I do based on success or failure. So in this case, our process manager can say, oh, if the message is successful, I'll go ahead and publish out an event. But if it's not successful, then I need to mark the order as being failed, and then there'll be some background intervention remediation process to call the customer and say, your credit card failed, can you please give us your information? And so the downstream systems, because SendGrid and the other downstream services don't have any coupling with each other, then I can actually piggyback on top of that initial RabbitMQ message to say, SendGrid is now just another subscriber of that same payment successful event. So sending the email is now just yet another subscriber of everything else in my process. So SendGrid received the order accepted event, sends the thank you email, and all the downstream systems receive that event more or less, concurrently, and they're doing the processing as well. So this is a more complicated picture, right? We've taken those 6 lines of code and now distributed them amongst multiple endpoints and different services who are solely responsible for doing that set of work and nothing else. But now we can more gracefully handle failures between each of these different systems by explicitly having logic in our process manager to say, here's what to do when things succeed or fail. Now, back to Bill and I, what did we do? Well, we didn't do this because we only had 2 weeks to launch. So we actually stopped about 30 minutes ago in this presentation of doing the authorized capture step. That was like the easiest thing for us to ship. But if we had some more time, we would go to a much more robust processing system to ensure that we were able to get the highest degree of success of calling our of processing orders. So any of these options are viable depending on your business needs. So it is important for us to go back to the business to say, based on our timeline and business needs, these are the things that we actually need to do. So that was 6 little lines of fail. You can find this presentation on my GitHub at github.com/jbogart/presentations. If you want some more information about all the patterns that I've talked about today, they all actually exist in this book called Enterprise Integration Patterns, which should really just be called messaging patterns, because that's what it is. But all those patterns that I went through today are described in much more detail inside of that book. Okay, so the first question was, what are your thoughts on callback architecture? And I'm guessing that's having to do with the kind of the webhook callbacks. I think, and if I'm wrong, by the way, you can hound me on Twitter later. It's okay. The thing I don't necessarily like about that, it's difficult to understand how my system is put together. I tend to like more of a pub sub based model where I have a known set of things that I can subscribe to versus the callbacks that we have there. The next one we have is, how does serverless architecture, scroll too fast, affect these considerations? So for me, serverless is about the deployability of each of those different endpoints that all those boxes I have available to me. But otherwise, serverless architecture, what it allows me to do is to make those boxes smaller. So the idea of having a messaging endpoint listen and receive and send messages, now that can be an Azure function that does that, as opposed to this thing I got to deploy to a container or something like that. The same thing with API. So it doesn't necessarily affect the logical architecture of how things communicate with each other, but can affect the physical deployment of each of those items. I got one about event-based reactive approach used in the applications, or should you use it in some cases? I do like the event reactive-based approach especially for kind of desktop applications with in-memory messaging. I do find though the reactive code is one of those things that's like, it's written once and never modified because like everything has to be just right for everything to work. But otherwise it can make things a little bit more explicit and declarative as opposed to imperative. With messaging though, I don't tend to use that sort of approach as much because each handler I find lives very much on its own, and I'm not doing a lot of custom processing with the message content itself, or doing content-based sort of things. This message comes in, here's the block of code that executes it, and that's done. There's a statement, which is, the world would be much better if every service had a health check endpoint. Sure, the world would be much better. The difficult part is for messaging endpoints, it's difficult to know if a messaging endpoint is healthy or not. So it's easy for API endpoints. I can send a ping to an API and they can respond. But for something that's just pulling messages off of a queue, that can be a little bit more difficult to tell if it's like healthy, quote, healthy or not. So for those kinds of systems, I actually have different kind of metrics available to me that I use, things like cycle times and processing times. Like My SLAs for messages say when I send a message to when I process it should be no more than 6 hours. And so I have something that's looking at messages getting processed to say, how long has this message waited in the queue to be able to be processed?